Hi guys, and welcome to tonight's live training from Drayton. Thanks for joining me on what is quite a miserable day. Certainly here it is. It's rain, but it's not as bad as some places. So I hear with all the snow. But tonight we're going to have a look at these again. We've been doing quite a bit on these recently, obviously, because this is our new product. This is the Drayton Balancing Key 𝗵𝗴. And as I've really said in the promo, I've done quite a bit on these already about how you set them up and the sort of benefits to the customer. But we've been getting a few questions about wanting a bit more detail on the sort of the back end and the sort of the science behind them and how they actually work and how you can sort of be a bit proactive with calculating flow rates and that through your system. So that's really what I'm going to cover off tonight. Usual sort of format. So if there's any questions as we go along, I'm going to be monitoring them. So this will probably go on for about half an hour. That tends to be what they run for. So you've got a chance to get any questions in about this, or indeed anything else that you see that you just want some advice on. So I'm going to kick it off by firstly just going through again why we need to balance. I know that I've sort of done this subject a little bit to death, but I am still getting questions on it, and why there is a requirement to balance your heating system. So I'm going to kick off with that, and then once we've done that, we'll have a look at some of the science behind it. I'm going to take you through the mass flow rate calculation. And I promise not to melt your head with it, because I sort of did mine earlier on when I wrote this. So I've tried to sanitize it as much as I can. But that's really where we're going to go tonight. So let's kick it off, and I'll take you through with this little presentation here on why we balance our heating system.
Why it's important for us to have a balanced heating system. And here we have a mock-up of a boiler and some radiators, and in reality these radiators will be all in different rooms of the property. They're all likely to be different sizes to accommodate the output requirements of the respective rooms, and they're all going to have different lengths of pipework feeding them from the flow and return from the boiler. But what that all amounts to is that no two radiators are the same in terms of their resistance to flow. And what you tend to find is that the radiators that are closest to the boiler tend to have less resistance to flow than ones further away, and balancing looks to even this out across the whole of the system. To do this, we need some way of restricting the flow into the radiators, so we fit some valves. Now, it doesn't matter whether the radiators are being controlled by manual valves, whether there's a lock shield at either end, or whether at one of the ends there is a thermostatic radiator valve. Ultimately, a radiator system needs to be balanced regardless of the method of control for the actual radiator itself. Once the valves are in, we then add some pipe work. So this is our flow, this is the hot water leaving the boiler, and then we've got the return, which is the cooler water, once it's been through the radiator, going back to the boiler. Now, you'll hear the term delta T referred to when talking about balancing a heating system, and what that means is differential temperature. That is the difference in temperature between the water leaving the boiler on the flow and what is coming back to the boiler on the return. And typically, most boiler manufacturers recommend a delta T of 20 degrees for the boiler to run at optimum efficiency. So what we're looking to achieve by balancing a heating system is that as the hot water leaves the boiler and approaches the T for any particular radiator, there's no greater or lesser resistance for the flow to go either through the radiator or to carry on in the flow to fulfill the heating requirements of the other radiators downstream on the circuit. And this way, we're ensuring that all of the radiators on the system are getting sufficient amounts of hot water to achieve their heat output. Now, here we have a scenario where the system is out of balance, and this first radiator, it hasn't been balanced, so the valves are wide open. So as the hot water leaves the boiler and approaches the T, it now finds that the path of least resistance is to go through the radiator, and therefore it doesn't allow the water to flow on to the rest of the radiators on the system. This causes two main issues. Firstly, other radiators on the system don't receive enough hot water, so they're unable to achieve their heat output, and that will result in cold rooms. And this will be particularly apparent on those radiators furthest away from the boiler, or where the hot water has needed to be elevated to higher floors. And secondly, this short circuiting will allow the return temperature to increase much quicker than it would normally. So you've no longer got a delta T of 20. And it's highly likely that the return temperature will rise above 54 degrees, which is dew point. And that will mean that the boiler will no longer be in condensing mode, severely impacting boiler efficiency.
Okay, so that's why we do it. And that's really talking in terms of the old-fashioned way of doing it, where we've got a lock shield valve at the other end, and we're adding resistance to the system by throttling down the aperture inside here, which is still a viable way of balancing, but it just means it's a little bit more fussy in so much as it's quite iterative, because you have to do each radiator at a time, and you're really having to measure the difference between the flow in and the flow out of the radiator. Now, one of the things that makes balancing either a chore or much easier is something called valve authority, and that essentially means the amount of resistance that's sort of built into a valve from the get-go. So before you even start modifying the shape or the size of the aperture, some valve bodies will inherently have a greater valve authority. And what I mean by that is, if you look at this lock shield here, you can see this is a standard lock shield, and the ports on this are wide open. So you've got really large ports either end. And you could quite easily use this lock shield with one of these, which is our EB body. But you can see that this EB body has much greater valve authority, even in the wide open position, just because there is more resistance to flow. There's more stuff in the way that prevents flow or restricts flow through the valve before you even start modifying your aperture. Now, what that actually means is that if you use something like this to do your balancing, the difference between this valve being wide open and fully shut is only about 2 turns, even though if you were to wind the cap on that, it would wind out maybe sort of 10 to 12 turns. You're only really working in the sort of bottom couple of turns, and again, that makes it quite difficult to do, because you haven't really got that much room to play with between the valve being wide open, which is essentially going to mean your radiator or any radiators that are closest to the heat source are going to be able to balance if they've got the potential to sort of rob that heat because there's no resistance, right down to it being throttled off. You haven't got that much difference. So valve authority is a really big deal when it comes to trying to balance the system. You've seen the EB body before, the one I just showed you, the one that you can actually turn the insert on the top to 6 different positions, and that changes your aperture size. So as well as changing that aperture size, you've also got this built-in resistance from just having a 6mm hole in the output. And then if we have a look at the auto balancing body, you can see at first glance it looks like it would have low valve authority because it's quite wide open, but the key thing is that little element at the bottom there. Now that's your pressure independent element, basically saying that regardless of what system pressure changes on the system, you will get a consistent flow rate through the radiator based on the setting that you set on the top of there. Now, if you remember that these here go from 1 to 15, and that's 10 times liters per hour. So position 1, 10 liters per hour, all the way up to 150 liters per hour. Now you can set this using the box on these come in. They've got a little table if you already know what the output of your radiator is, or you can use the online calculator where you can measure the radiator, put in the type, and it will tell you. But I'm actually going to take you through some of the maths on this so that you can sort of sensor check what's going on, and it's not just me sort of telling you that they work. This is actually, you can see where the science has actually come from. So there's going to be a bit of maths and a bit of algebra, but I'm going to sort of take it pretty slowly and sort of walk you through it. So this all really comes down to mass flow rate, and this is the mass flow equation. It's m dot is equal to dm over dt. So it's basically just saying that your mass flow rate is a function of both a change in mass and a change in time. So it's really just a calculation of how much either liquid or gas, because this is sort of real top level equation. It's liquid or gas, how much passes over a given time period. Now, that in its current form doesn't really do a lot for us. So what we need to look at is we need to look at our variables, the sort of things that we're actually interested in, and that's these. So obviously flow rate, that's what we're trying to establish, and that's going to be in liters per second. You've got your heat output, which is measured in kilowatts. You've got your difference in temperature, which will be in degrees Celsius, and that's where your delta T is going to come from. And then the one that sounds complex is the specific heat capacity, which is joules per gram per degrees centigrade. Now, whilst that sounds complex, it's not too bad because it's actually a constant. Because if you're using, say, water, it will change for glyco because each medium will have its own specific heat capacity. But for simplicity, if we use the specific heat capacity for water, it's a constant, which is, I believe it's 4.186 joules per gram per degree centigrade. So what that's actually saying to you is that to get a gram of water, to elevate the temperature of that gram of water by 1 degree, it requires 4.186 joules. Now, for simplicity, we tend to simplify that to 4.2. It's, you know, the numbers we're dealing here, we don't need to be super accurate, so we can afford to round that up to 4.2. But the way that these actually all work with each other now, if this is going to progress on for me, there we go. This is actually the equation. So the flow rate is equal to the heat output divided by the specific heat capacity times delta T. So heat capacity we'll know because it will be stated on your radiator. And again, this is really where the science is coming from behind what's actually driving the chart that's on the box and also the parameters that you put into the online calculator. So it ends up being heat output divided by specific heat capacity times delta T. So we know the heat output, we know the specific heat capacity of water is 4.2, and we know our delta T, which is typical industry standard, is 20 degrees. But remember, the box can do 10 degrees or 15. But armed with this calculation, you can choose a flow rate of, or you can choose a delta T of whatever you want. And you can then be a bit more tailored with your flow rate. Even though we just give you the 3 on the box, you can do a bit more legwork if you want with this. So what this actually sort of boils down to is heat output divided by 4.2 times 20, or heat output divided by 84. That's with a delta T of 20. Obviously, if it was a delta T of 10, it would be 4.2 times 10. So it would be heat output over 42. So you don't really need to remember any of the algebra or any of the maths. All you really need to remember is your heat output divided by, if it's a delta T of 20, 84. And from that, you can then calculate what's going on and what flow rate you need for a particular size radiator. So if we take an example here of a 700 watt radiator with a delta T of 20, there's going to be flow rate is equal to 0.7, because remember the heat output, the units that are used there are kilowatts. So it's going to be 0.7 kilowatts divided by 8.84, and that is equal to 0.008 plus some change, and that's going to be liters per second. Now, obviously, liters per second is not hugely useful to us because none of the sort of increments on the valve show you that. We need to get it into liters per hour. So it's just a case of multiplying by 60 to get into liters per minute, and then multiplying by 60 again, which gets you into liters per hour. So what we're saying here is for a 700 watt radiator at 20 degrees, a delta T of 20 degrees, it's 0.7 divided by 84 times 60 times 60, 30 liters per hour. And if you look at the chart on the box or you look at the calculator, it will tell you that that's what you need. You need to set the valve. And let me come back into the room if I can. Here we go. That's telling you that the setting on the top of there would need to be set to position 3. Position 3, remember, this is 10 times liters per hour. So position 3 is 30 liters per hour. So to make balancing as easy a job as possible, you can go around with your lock shield and you can start throttling these down and doing your differential temperature measurement across the flow and return, and really where you're sort of adding resistance to a radiator and you're using the temperature difference to sort of equate to different flow into the radiator. But it's much easier if you use these, because remember, if you set this at 30 liters per hour for, say, this 700 watt radiator, it will be 30 liters per hour that is flowing into that radiator, regardless of pressure changes on the system, which can arise from other valves shutting down, or just the temperature going up in the system. So really useful, and hopefully you armed with that equation, or just the idea of heat output divided by 84. If you're doing a standard 𝗫𝗀 of 20, you'll be able to calculate what flow rate you need into any particular radiator. So with that, there's a few things that we need to, a few system design considerations and a few best practice with these valves that we need to consider. And this is really just picking up on some things that some questions that have been out, or some challenges I've had from people that have been using these. The first thing is that they are unidirectional. So if I zoom in a bit on that, you can see that this is the 15mm angled body. Now, we're used to the sort of line that all of Drayton's angled bodies are bidirectional. Well, these aren't. These are unidirectional, meaning that you need to respect and follow the flow direction arrow. And the upshot is, if you don't, and this is what I've sort of been hearing from customers, if you get them in the wrong way around, they are quite new. For the start, you don't get the right amount of flow into the radiator, and they can be noisy. So you really need to make sure that you respect that flow direction arrow. It's exactly the same on the straight. I mean, the Drayton straight valves have always been unidirectional, and that's really just because of the way that they're constructed. You can see that the ports at either end are completely different. But with angled, it's not a 15mm angled always used to be bidirectional. These aren't. So you can't just blindly go in and retrofit to radiators and replace like for like, without doing some measurement of which is your flow and which is your return. So kick the heating on and establish which is the flow and return. These can go on either the flow or return, but if you want the sensing head to sit vertically, as we're sort of used to in the UK, then this has got to be on the flow side, because it's got to flow out of the floor and into the radiator. If you fit these on the return, which you can do, but it means you've got to roll the head over, and you've got to have the sensing head sat on its side so that the flow comes out of the radiator and back into the floor, respecting that flow direction arrow. So flow direction is a key one for these. Also, if you're going to be fitting these, because of, and again, this comes down to it having high valve authority, the aperture inside is very small. So you want to make sure that you're fitting these to a clean system. And ideally, you want to be flushing your system first, but flush it with the old bodies in. Now, there's some talk about us having a tool where we can extract these inserts. Now, this is not something that's live at the moment. It's just something that's being talked about. So that in the future, once you've had these in for a while, if you then want to flush your system, you'll be able to extract the insert and flush your system without having to physically remove the bodies. But in the meantime, flush with your old bodies in, and then once you've got your system nice and clean, that's when you can stick these in. So that's another sort of top tip. And lastly, the question comes about, how do we maintain constant pressure through these? So how do these essentially work if you've got a pump that modulates? Now, we're quite used to modulating flow temperatures with things like open therm. But if you've got some system boilers, they will have what are called burner linked pumps. And what that means is that as the demand decreases, the pump speed will decrease, and you could get to a scenario where if you've got this set to say 50 litres an hour, you might not be getting that through your pump. So it appears that your system would then go out of balance. Now, that is sort of true in so much as you won't be getting consistent flow rate into each radiator as per your setting, because there is just not enough flow there. But by that time, the system will have modulated down, and so it's unlikely to harm your efficiency too much. But what I would say is, I would strongly advise using these with a fixed rate pump. So something like, if you've got an external pump, you'll be fine. And if you've got multiple pumps on the system, and also if you can steer your system away from modulating the pump speed, so having a fixed pump speed, that would be really beneficial. And that's going to make sure that you're going to be getting consistent flow rate through these bodies as per what you set on the dial. But if you haven't got the flow rate in the first place, you're not going to get it. So that's really my sort of top tips based on what I've seen come in over the past sort of few months that we have had these that these have been live. I'm going to just flag that this will be sort of maybe like the last maybe 2 or 3 minutes of this session. So if you've got any questions, I don't see anything come in as it stands, but if you've got anything, this is sort of your sort of last warning to get them in. In the meantime, what I will talk about is some stuff on the 9° network. So let me pop this up. So we've got obviously the priority shop that you're all familiar with. And the current deals that are on in there is 40% off the Wiser kit. So you've got multi-zone kits in there that are 40% off. We've also got 40% off the underfloor heating for wet underfloor heating, the Wiser underfloor heating controller, and the Wiser electrical heat switch. You can also get your remote temperature sensor there for the electrical heat switch if you're using it with an electric underfloor heating mat, or if you want to have a single zone controlled by that using the wet underfloor heating controller, the Wiser underfloor heating controller, that one there. And it's also a place where you can get valve bodies or auto balancing bodies as separate. So this was a question that came on the group the other day: is if I want to use it with Wiser, do I need to buy box kits and throw away heads? Well, you absolutely don't need to. You can buy them as separate. So there you see the angled auto balancing body and the straight are available as separates, as well as other TRVs and the Digistat range. You can also get the EB body as straight and angled as separates without a head. So you don't need to be buying packs and throwing sensing heads away. Whilst I'm on here, I will also show you the 9° Academy, because there is a new module up there which might be of interest to you. So we've already had Wiser TRV and the new Digistat. Well, there is now the motorized valves module. So it's about, I think it came in as being sort of an 8 or 9 minute video. There's no questions or anything, so it's really just for information. But it takes you through our motorized valve range, and I also do some bench testing as well. So if you've got some valves that you're not sure whether they're working as they should, there's a little section there showing you what happens if you power up each wire and how to test to see if the end switch in, say, like a ZA5 or something is making or breaking. So really good module. In the future, sort of coming off the back of that, there is going to be a module on how we build a system. So sort of a controls approach to building up a system. Obviously, a lot of it's always focused on getting the boiler in, but you really want some sort of like best practice to fit your controls. So that'll be that. And then once we've built the system, we can then fault find on it. So I'll be taking you through all the different ways of fault finding, doing some live testing. So that will be quite a chunky module, as well as some there will be some updates to the existing modules up there. So this mass flow rate calculation will find its way onto the auto balancing module, and we're going to revise some of the Wiser bolt-on modules like the underfloor heating, and also some of the other animation ones are going to be revised in line with the new app, and just changes that have happened on the Wiser platform. So I don't see any more questions, so I'm going to bring this to a close. Thanks for joining me tonight. Keep an eye out on the group for the promo videos of what's coming up. I think Claire's got something going on with one of her panels that she does with her expert panel. I think that's maybe the next thing that's coming up on the channel, on the group. So keep an eye out for that. They're always good and really insightful. But thanks for joining me tonight, guys. Any questions, stick them in the comments. This video will end up on YouTube as well as on the group, and it's always monitored. So if you're not watching it live, but you've got some questions all the same, just reach out on whatever platform you choose, and I'll do my best to answer it. Until the next one, which is probably in a month's time, thanks for joining me, and I'll catch you soon.